Okay, the purpose of today's class is to very briefly review some of the key concepts of signals and systems, something that you learned in 345. We'll go over, we will not touch upon all the concepts that you learned, but just some of the basic ones. So mathematically, we'll try to understand what is a signal. So a signal, mathematically, we understood the meaning of a signal in terms of just our understanding, but mathematically it is a function of one or more independent variables. And the function takes either real or complex values. Okay. So one or more independent variables means we'll call the signal, it's a 1D signal, 2D signal, 3D signal. There are n dimensional signals. So what an ND signal, typically we write it as x of t or s of t or x of whatever. So a common example is speech signal. It's a signal which is varying with time, just one dimension. There are examples of 2D signals. For example, the signal I could write as f of xy, so it's a function of two variables. And an example is temperature as a function of longitude and latitude. So x could be the longitude, y could be the latitude, and you are saying what is the function value at each longitude-latitude pair, right? There can be 3D signals. For example, it could be G, X, Y, Z, and that could be pressure as a function of longitude, latitude, and let's say elevation, and so forth. You can have n-dimensional signals where you can keep on adding things. For example, you can make a signal a concatenation of the temperature and the temperature, right? So you can have a signal which is composed of other signals. Now the signals, so these are just signals which are given by variables, independent variables, and they take real values. You can also have signals that take complex values. So you can have complex signals. You can, for example, write x of t is given by a real part a of t plus j b of t, right? So both a and t and b of t are real. And so together you have this complex part, a of t plus j b of t. Now, the most common place where signals like complex signals appear are, for example, in communication systems. If you think of MRI machines, the signals in MRI machines can also be described as complex signals. Now, what is, it's a little bit of a, unfortunately, I don't really like the term when they say real and complex. It's as if we are saying that the complex signals are not real anymore, real in the sense of what we perceive the world to be, right? That's not the right notion. Complex signals do exist in the world, right? They are all around us. And if you want to think of the complex signals, while mathematically we can describe them in this polar diagram and all that, if you want to think of the complex signal, the one way to think of it is it's a signal which has two pieces to it. One is the real piece, and one is the one that is associated with the imaginary part. And the two pieces can't interfere with each other. So in communication systems, when you will later learn, you will, for example, learn about something called in-phase and quadrature phase. I mean, your cell phone literally transmits these complex signals. Let's say it's an abstraction of the real world, okay, where you have two pieces of the signal which don't interfere with each other. Now, in this class, we'll do only 1D signals. And in these 1D signals, we'll, as an example, take the independent variable to be most of the times as t, which is time, but that could be the general rules that we'll study for 1D signals. They are not a function of whether we are talking about time. For example, I could be looking at a signal which is just measuring the temperature at the edge of this room. So that's 1D signal. There is only length, right? There is no difference between that, whatever things we learn, and a time domain signal. Okay, we'll still call that a time domain signal, but in reality, it's a spatial signal. 2D signals or other forms of signals, you will learn about them in the more advanced elective course. There's a DSP design course that is taught in spring of senior year. You will learn about that there. Now, when we talk about signals, there are two main, we can divide the mathematically signals into two types. So previously we talked about just in terms of our common sense, what are the two divisions, man-made and synthetic. Two main types of signals also exist when we are talking about them mathematically. The first type is continuous signals. And we'll write them x of t, s of t, whatever, doesn't matter what notation we use. And what is a continuous signal? A continuous signal is described by the properties of its independent variable. So if this independent variable takes all possible values in a continuum, then we call that signal a continuous signal. So t could take a value between, we could say, well, t takes a value between -1 and 1, and it's a continuous signal, which means that it could take a value 0.000004, or you can keep on going. Okay? It takes all possible values in a given range. Okay? Now, the other types of signals are discrete time signals or discrete signals, and we commonly write them as x of n, y of n, and so forth, z of n. Now again, the thing that describes whether it's a discrete signal is it's the independent variable that describes that signal. So in that case, the variable n takes only a discrete set of values. Now, more commonly, since it's a discrete set of values, and we can just replace that with the set of all possible integers. So we say that n basically is 0, plus minus 1, plus minus 2, and so forth. Okay? So the signal is only defined on n equal to 0, plus minus 1, plus minus 2, and so forth. And what that means is that a discrete signal is nothing but a sequence of numbers. It's nothing but a sequence of numbers. You collect a bunch of numbers together, and that becomes a discrete signal. For example, if I order the roster of this class according to alphabetical order, and then I say, well, I'm going to record the final marks that you obtained on ECE 345 final, right? That is a collection of numbers. That's a discrete signal. Simple as that. It's a function, or it's a function of, for example, I can translate it into your UID numbers or whatever. That's a discrete signal. Now, a discrete signal means that it only takes values on a discrete set, which means that, for example, x 0.3. It's not that, well, x 0.3, maybe it's 0 or 1. It's not even defined. There is no such, I can't define the function on x 0.3. Okay? So this doesn't exist. So that's the basic distinction. A continuous signal takes it takes values on all possible values of its independent variable. A discrete signal only takes values on a discrete set of points. And it's nothing but a sequence. Okay? Now, when we talk about continuous signals, sometimes we also talk about analog signals. So, what is the difference between continuous signals and analog signals? Continuous signals, strictly speaking, although we often mix the two terms, strictly speaking, a continuous signal is only saying that t takes all possible values. Whereas when we say it's an analog signal, it means that the values it takes are also continuous. The amplitude of the signal is also continuous. So it's continuous signals with continuous amplitudes. Okay. And sometimes when we talk about discrete signals, we again mix the terms. We sometimes say digital signals. What is the difference? Strictly speaking, although we mix the two, that not only n takes values on a discrete set, but also the values that it takes are also finite. Okay? I'll explain that a little bit later. So discrete signals with discrete amplitudes. Strictly speaking, they are not the same thing. So here is an example of, let's say, this is my x of t. So t is going to infinity. Of course, my signal is defined on all possible values of t. So it's a continuous signal. And the amplitude that is taking is also taking all possible values in a certain range. Of course, it doesn't have to take from minus infinity to infinity, but between this range and this range, whatever is the number, let's say this is 2 and this is minus 1, it's taking all possible values. It's passing through all values. So this is an analog signal, a continuous signal with continuous amplitude. You could also have this signal okay. This is again t is going to infinity. This is, let's say, this is plus 1 and this is minus 1. Strictly speaking, this is a continuous signal but not an analog signal. Why? Because it's taking values on all possible values or on all possible values of t, but the amplitude is only taking two values. It's taking either minus 1 or 1. Right? So a little bit of a distinction. Similarly, when we talk about a discrete signal, x of n, We define it for n equal to 0, 1, -1, -2. So if your signal can take all possible values in this range, right now I'm drawing only 5 values, but let's say these 5 values could be any number between 0 and assume 2. So this is a discrete signal with continuous amplitudes. This is not a digital signal. Whereas a digital signal will be, if I say that the values that it takes are only a discrete set of points. So let's say I say that the signal only takes values 1/2, 1, -1, -1/2, and it only takes these values, it doesn't take anything else. Maybe it can take 0, but nothing else. So now the amplitudes can only take a certain finite number of values, and this is a digital signal in the strict possible sense. N is discrete and the amplitude is also discrete. So that's just a brief understanding of the terminology of signals in terms of mathematics. Now let's talk about systems. We already described a system as something that takes an input, produces an output. Now in this class we'll talk about systems. We'll talk about single input and single output systems. Or they are commonly called CISO, which means that they take only one signal as input and produce one signal as an output. Okay? Of course, there are systems that are not really CISO. They take multiple inputs. They may generate still one output. A very classical example is, for example, ECG signal, right? An ECG system. If you have ever seen people with ECG probes, right? They have more than one probe. So those are all the signals that are coming into the system. So it's a multiple input, but at the output, they generate that ECG plot. Right? So it's one output. So ECG, and you can think of many other examples where you have multiple inputs. But in this class, we'll stick with only one type of a system, which is CISO. Okay. Now, a system can take any of the either a continuous input and produce a discrete output, or any combination thereof. So you could have a system which has, so here are input, here is a system which is sitting in, let's call that system T, and here is the output. So you can have a system which is taking continuous input and generating continuous output. An example of that is a cell phone. Takes in voice, which is continuous, generates RF signals, which are continuous. Another case could be that it's taking discrete input and generating discrete output. An example of that is most of the things that you do inside your computer or your cell phone only. So for example, if you are taking an image, which is a discrete signal, and doing some photoshopping to create another image, it's a discrete signal. So discrete input, discrete output. You can have a continuous input, but a discrete output. What is an example of that is a digital voice recorder. You are using voice, that's continuous. You are generating an MP3 file, that's discrete. And the last example is you are taking something which is discrete as input and generating a continuous output. An example of that is an iPod, for example. Right? It's using a digital file, an MP3 or whatever, and then it's producing music which is continuous time. Okay? So a system can have any of these forms, and to describe a system, you need to know the input-output relation between every possible input and every possible output for general systems. But that's too complex. So to simplify the world, we look at the simplest and most often used forms of systems which are called linear time invariant systems. So we'll talk about why do we like the linear time invariant systems so much, but let's first ask ourselves what do linear time invariant systems mean, or as we call them, LTI systems. Well, an LTI system is composed of two pieces. We are saying it's linear and time invariant. So let's look at the class of systems which are just linear. So what is a linear system? Okay. A system can be non-time invariant but still linear. So a linear system is simply a system that satisfies the principle of superposition. What does that mean? That if you input x1 of t and your system generates an output y1 of t, and if you input x2 of t and it generates output y2 of t, okay, then any combination of inputs should generate the same combination of outputs. So if I have a superposition of inputs. If I say that a x1 of t plus b x2 of t is my input, then my system should generate a y1 of t plus b y2 of t. Now this should hold for all possible input combinations. A system which satisfies this property for, let's say, 2 or 3 inputs, but not for others, is not a linear system. Just because it satisfies the property on two signals doesn't make it a linear system. A linear system is something that produces this superposition property regardless of what the input is. Okay? Now, what's the most common example that you can think of a linear system? Let me give you another example of a linear system. Let's say you have a mic and you are generating from that, the mic is recording something and you are generating that on a loudspeaker. Okay. Now, if I speak on that mic, you hear something. If one of you speak, you hear something else. But if both of us simultaneously speak, what happens? You hear the same output superimposed on each other. Right? So that's a linear system. Circuits without any active elements, they are typically also linear, right? So linearity is just, it obeys the superposition property, but it has to obey it for all possible inputs. Keep that in mind. Now, the second part of LTI systems is time invariance. So, what's a time invariant system? A time invariant system is simply a system that we are saying the system is not changing with time. It is static. The operation of that system does not vary with time. Okay? That's the intuitive meaning of a time invariant system. So what it means is that the output depends only on the input and not at the time, not on the time at which it is applied. So mathematically, what it means is that if my input is x of t, I have a system t, and I generate y of t. Now instead of applying that input, I apply that input, let's say, 2 days later. So I apply that input x of t minus sometime t0, where t0 is equal to 48 hours. Right? The system's output should still be the same. The only difference should be now the output will be produced 2 days later. So the output will be exactly the same, but it will also be shifted by 48 hours. Time invariance is a very important property. It says that the system is not changing its behavior over time. If I speak into the mic and you hear something, and if I speak into the mic 2 days later, the same thing, you should hear the same thing out. That's a time invariant system. Another example of that is, let's say I take an image and I run it through a Photoshop to do some operations, generate another image. Whether I do that today or I do that input 10 days later, it will result in the same. Your microprocessors, they are to a large extent time invariant. If you run them today, some software, they produce the same result. You run them a year later, they produce the same result. Right? And just keep in mind, as I said earlier, if a system produces the same output, time invariant output, but only for 1 or 2 inputs and not for all inputs, then that doesn't make it time invariant. Time invariant means that it does the same for all possible inputs. Okay? So what is an LTI system? An LTI system is something that is both linear and time invariant, so it has to separately satisfy both of these properties. Most of your circuits, for example, will be time invariant up to a certain scale. Of course, we know that circuits change their characteristics if you increase, for example, the temperature too much, right? But up to a certain level, we'll say they are time invariant. Now, just because something is linear and time invariant, why does it make us love LTI systems so much? Here is the reason. In general, a system, to describe a system, what is the behavior of a system? We have to know how does the system behave on every possible input. What is the response of the system on every possible input? But if you are a time invariant system, then something amazing happens, which is that output to every possible input can be specified as long as we know the output to a special input. This is a property of LTI systems only. If you know the output to a special input, you can actually specify the output to every possible input. That is really amazing if you think about it. So what is that special input? That special input is called the delta input for continuous time signals, denoted by delta t, or the impulse input or direct delta input for delta. So the impulse input, which is denoted by delta n. So delta t, of course, on a continuous time it looks like this. This is delta t, which is defined not in terms of its value but in terms of its area, that the area under the curve is 1 at t equal to 0, and everywhere else it's 0, whereas for delta n it's defined as at n equal to 0 it takes the value 1. Right? So if you know the output of an LTI system to this special input, this input in general we call it just an impulse. So if we know what is the output of the system in response to an impulse, so if I input delta t, let's say the response I get is h of t. Or if I input delta of n, let's say the response I get is h of n. And what do we call this response? As the name implies, input is impulse, there is a response, we call that impulse response. So we call this impulse response. Keep in mind, every possible system, whether they are LTI or not, has an impulse response. The question is whether knowing the impulse response is enough to know the output of every possible input. And that is a property of only an LTI system. If you know the impulse response, then for a continuous time LTI system, if you input now x of t is input, then output is given by y of t equals x of t continuous convolution with h of t. So continuous time convolution. And if you have a discrete input, discrete output system, then y of n is given by x of n, discrete time convolution with h of n. So this is discrete time convolution. Okay. So it is the unique property of LTI systems that if you know their response to a special input called the impulse response is enough to specify outputs to every possible input. Okay. And that's why we like the LTI system so much. Now, of course, you guys did continuous time and discrete time convolution. It's just a reminder, the continuous time convolution, the reason it comes up as we talked about it is because they help us specify, convolutions help us specify the outputs of LTI systems. The definition of convolution is, for continuous time convolution, y of t minus infinity to infinity, x of t minus tau, h of tau, d tau. Of course, tau is a dummy variable. You can replace it with whatever you like. And you can express it the other way around too. You can replace the role, you can switch the roles of x and h. So you will get the same answer, h of t minus tau, x of tau, d tau. Okay. And algebraically, you should think of it what is called the flip and slide rule. So mathematically what is this saying? That the output at time t, to compute the output at time t, you multiply, for example, your impulse response if you want to use this version, or you multiply your input if you want to use the second version with x of t minus tau, right, which is a flipped and time-shifted version of your input. You multiply the two, you take the integration, calculate the area under the curve. That is your output at time t. So here is a visual of convolution where we are using the version of minus infinity to infinity, h of t minus tau, x of tau, d tau. This is y of t. So they have given you x of t is this just unit step, and h of t is this decaying exponential. Right? So if you want to compute the value at time t, the first thing is, if you look at this, so this is, you have to flip h of t. So you first write h of minus tau, which is the flipped version, right? You are just flipping it around the axis, tau axis. So this is h of t, this is h of minus tau. This is the flipped version. Right? Now, if you want to compute the output at time t, then you basically just shift your h by time t. So if you want to compute y of t1, right, then you have to shift this flipped version by t1 minus tau. So one example is if I am computing t1 for some negative value, if I'm computing t1 for less than 0, right, then this is what the shifted version will look like, and then you multiply the two signals, and of course the multiplication of this, there is no overlap, you get 0, and then you compute the integration. So in this case, y of t1 will be equal to 0, and because there is no overlap, so when you multiply the two, you will get all 0, and the integration will be 0. If I am computing y of t at t equal to t2, then I shift it, and t2 is some positive value, then I'm going to shift h of minus tau to the right. Then I multiply h of t2 minus tau with x of tau, and this is what I get. This is the multiplication, everything else will be 0. And then I compute the area under the curve. This is the area. So whatever is the value of this area, that is my y of t2. And similarly, you can do it for t3, t4, and then you just plot it for every possible value of t1, t2, t3, and this is what you get, y of t. So this is what your convolution will look like. So this is just a graphical representation of what the convolution mathematically means. You can also use the other formula where h is fixed and x is flipped and either shifted to the left or to the right, depending upon the value of t. The discrete time convolution also has a very similar expression where all the continuous time things are replaced by their discrete time equivalent. So you have output y of n. The equivalent of integration in discrete time is summation. So you get summation instead of integration, but the rest of the thing stays the same. So you can have, for example, x of n minus m, h of m, and you are going from m from minus infinity to infinity. Compare the two formula, right? You have exactly the same form. Whatever is h of m, here you have h of tau, and the tau is going from minus infinity to infinity. In the discrete version, you have the summation going from minus infinity to infinity. You can switch the roles of x and h, and you can have h of n minus m and x of m. Okay? It is exactly the flip, and now instead of flip and slide, we can call it flip and shift rule for computing the discrete time convolution. Again, here is an example where we are using the version that y of n is summation m from minus infinity to infinity, h of n minus m, x of m. So we are keeping x fixed, and we are flipping and shifting h. So this is my h, This is my x. I'm going to first flip my h, so I get here in the diagram it's using the braces, but so I'll write it like this if you want to stay with the notation that we are using. So this is h of minus k, right? Which is just a flipped version of h of k. You just flip it around the y-axis. And now if you want to compute y of 1, if you are interested in computing y of 1, then you simply shift this by 1 to the right. So 1 is positive, so you shift this flipped version to the right. You multiply the 2, and you then add up all the values. So in the continuous time, we computed the area under the curve, that's integration. In here, we just add up all the values. So this is what is x of k, h of 1 minus k by multiplication of this and this. And then we sum all of the values, and that will be y of 1. Similarly, if I did not shift, so I have no shift, so I am effectively calculating y of 0. So I multiply these two, then add up, this is the answer that I get, then I add up all the entries, and this is my y of 0. If I want to now compute y of 2, then I shift my flipped version to the right. So this is for y of 2. I shift it to the right. I multiply it again with this x. This is what I get. Then I add all the values. I get 11, and that is my y of 2. Okay. So again, graphically is this version. You can also just compute it mathematically.